Welcome to the mini course on energy efficient electronics, searching for the Milli-volt Switch. This is a mini course on trying to come up with new types of transistors and switches that can work at low power and low voltage. I'm Sapan Agarwal. I'm a postdoctoral fellow at the University of California, Berkeley in the NSF Center for Energy Efficient Electronics Science. And so this mini course is going to be a series of 5 lectures on new types of switches and new ways to achieve low power electronics. This course is sponsored by the NSF Center for Energy Efficient Electronics Science. We are a large NSF Science and Technology center that's a collaboration across 5 universities. And our primary goal is to find new ways to achieve low power electronics. So why do we care about low power electronics? And it's really for 2 reasons. The first is that if you just look at how much electricity are electronics using, it actually becomes a significant fraction of just the electricity within the US. For instance, only data centers were already using 2% of the electricity in 2010, and that's projected to grow to 4% any higher. And so what that means is that even from the total global usage of energy, like global warming, electronics are a significant fraction. And that also means is that when you're trying to build data centers, the cost of electricity becomes so significant that companies like Google are actually building the data centers near cheap sources of power. In addition to just data centers, the power consumption becomes very important for individual electronic devices. If you think about, say, your mobile phone, that is already a device that can just barely last through the day, whereas we would like it to last for several days or a week. And now if you think about what's going to happen to electronics in the future, we're going to have more and more embedded electronics in everything. We're going to have smart grids. We're going to want to be able to dynamically manage our traffic using various sensors and monitoring. We want to be able to monitor our buildings, our infrastructure. And all of these are going to require sensors that require power. And ideally, we want these to last for months or years. But to do that, we're going to need very, very low power electronics. And so then the question becomes, how do we get these low power electronics? In the past, it was very simple. We would scale our transistors down, the operating voltage would go down, and then the power consumption would go down. And that's just because the power is sort of given by the capacitance times the voltage squared. But what you can notice is that in recent technology nodes, this voltage scaling has started to slow down, and it's actually approaching a fundamental limit. And so this means that we need to do something different if we want to get lower power. The problem is with current transistors is that there's actually a physical fundamental limit in how much voltage they need. And you can understand this by looking at how a transistor operates. There's a thermal distribution of electrons in the source. So what this means is that when we try to turn off the transistor, we essentially move this barrier up a little bit. And so now if we move this barrier up by kT, we then cut off our current by a factor of E, just following that thermal distribution. And so unfortunately, that means that if we want a large on-off ratio, we need a large voltage. So for instance, this factor of E per kT in voltage means we need 60 millivolts to get a decade change in current. And so that means that if you want a large on-off ratio, say 5 decades, we're going to need 300 millivolts to switch our transistor. And this is just a fundamental limit, which means that if we continue making transistors as we always have been, we're never going to reduce the power significantly. This means we need a new type of transistor. And so that's the goal of this course. In the first lecture, I'm going to talk about what are the fundamental requirements for power and what are the fundamental requirements on what we need from a good switch. And then in the following lectures, I'm going to talk about the different types of switches. So now there are actually 2 components to the power consumption in a modern microprocessor. There's the switch itself, and then there's the interconnects in between the switches. And typically in a modern chip, about 50 to 80% of the power is actually in the interconnects, while about half the power is in the switches. And so we really need to address both of them. In the second lecture, I'm going to talk about one approach for replacing the switch called a tunneling field effect transistor. And the idea here is that we're going to change how the switch operates from being thermally excited over a barrier to tunneling through a barrier. In the third lecture, we're going to talk about a different approach based on nanomechanics. And the idea here is that we're going to actually take a physical relay and physically move it up and down to open and close a switch. And potentially we can operate this at much lower voltage than a normal transistor because it's a completely different mechanism of operation. Now in the fourth lecture, we're going to switch gears and focus on the interconnect. The idea here is that in a normal microprocessor, the longer the wire is, the higher its capacitance. And this means that you're going to have a higher power consumption. If you have a wire that goes from one end of the chip to the other, it's going to use a lot of power. On the other hand, if we replace the interconnect with nanophotonics and use optical interconnects, it's the same amount of power regardless of how long the wire is. Once you generate your photon, it can travel as far as you want. And so for interconnects from one end of a chip to another, or between chips, we can save a lot of power by going to optical interconnects. In the last lecture, we're going to look at some technologies that are a bit further out. The idea here is that we want to look at nanomagnetics and use spin to both replace the switch and potentially use spin-based interconnects. And here, we're going to open up a large possibility of different types of devices that take advantage of new physics to give us new types of switches.